Hey everyone, thank you so much for watching the Henry AI Labs YouTube channel. I'm here with Dmitry Khan, the founder of the Vector podcast. And if you've been watching Henry AI Labs recently, I'm looking into making more content about the vector search engines and moving into the Weaviate podcast on the Semi YouTube channel. I've currently uploaded a couple of videos with Eddie and Dillacher where we discuss things like the HNSW algorithm, what the approximate nearest neighbor benchmarks are, and then miscellaneous use cases people have like image text alignment and vector search, and then the neuro-symbolic functionality and all these really cool things about the vector search engines that I'm really excited about. And so I'm really excited to be talking with Dmitry Khan, who also has a YouTube channel and is building up this podcast style content, and specifically about vector search, which I think is extremely interesting. That kind of niche focus with the YouTube channel. You know, the Henry AI Labs channel has been making videos just about deep learning in general. So I'm very excited to see like the narrow focus of the Vector podcast and how you plan on developing that and your vision for that channel. So with that, Dmitry, can you give us like some background about how you came to be doing this and how your interest on this developed?
Hey Connor, yeah, sure. Thanks for having me. It's a pleasure to be on your show. Yeah, as you mentioned, I started Vector Podcast like a couple of weeks ago, and really, I just woke up one day and I thought there is a void in this space. Like there is, of course, a number of players, vector database and researchers in similarity search. And there's a ton of publications as well, like research publications, blog posts, and whatnot. But like there was really no podcast or anything where you can kind of go and discuss in live mode, kind of some of your findings or get your questions answered. And so, because I was still learning this area, I really wanted to kind of connect with these makers. And so far there are a couple of episodes with Pinecone and Weaviate, and so few more are coming up. And I've been in this area for more than a year. Actually, it's my hobby, really. It's not something I do, for a living yet, but it's something that I enjoy doing. And I guess during COVID, I just didn't have anything kind of better to do, like many of us. And so I decided to drill into this. And I just got interested in first introducing vector search in Apache Solr, because Apache Solr was the system I've been using and customizing for many years, actually more than 10 years. And that was kind of natural segue. And then at some point it was a discovery. I've learned about existence of these vector databases and I was like, cool, there is so much going on. And I thought, maybe some of these databases are already production facing, maybe some of them are not yet. And that's how my discovery began.
So when you first, so were you working with say like TF-IDF and BM25 encodings of text, and then you found out about say like the Siamese BERT encodings of text? Is that kind of the transition where you? Because for me personally, that was when I was like, oh wow, there's something really interesting happening with particularly in the search space with deep learning. Is when I found out about the text representations.
Yeah, I mean, in my previous company, AlphaSense, we initially, yes, we used TF-IDF, looked at BM25, looked at some other ways to encode information in such a way that you can turn your search engine more like a question answering system. Um, but it wasn't very kind of easy way for us, and we thought, okay, what can we do? And then BERT came about, and we thought, okay, how can we use BERT? And so initially we used BERT in some other downstream task like sentiment analysis. And that was kind of embedded in the search experience and users loved it. But then we thought, okay, how can we add BERT kind of deeper in the search experience itself, right? During the query execution, can I use some features from BERT or maybe fine tune it to your domain? Like in our case, it was financial data, like financial documents. Yeah. So, like I would say maybe there was one GitHub repository that I found, and I think it was semi-abundant. But I thought I'll give it a go, and it was written in Java. It's like a query parser kind of plugin to Solr, and it was doing exact KNN. So it wasn't even doing approximate nearest neighbor search. It was doing just exact version of it. But I still thought, okay, I'll give it, a spin, and I basically ported it to more recent Apache Solr version, I think from 6 to 8. So it was quite a jump. It took me a few weeks to figure out some things, even though it's just vector data, but the dynamics and mechanics of things, inside Solr. They're not very kind of straightforward. Anyway, so with some help from Adrian Grant, hey Adrian, if you're listening to this, he works for Elastic and he's an Apache Lucene committer. And so he gave me his hand on Twitter actually, and just mentioned a few things what I can do to kind of progress on this task. And then like I also set a deadline for myself, because like how you can easily go into this rabbit hole type of tasks. And I was thinking, I have just 4 hours, right? So if within 4 hours I get some results, then I will blog about it and let's see what happens. So I'm basically satisfying my curiosity in a way, but at the same time kind of probing the limits of possible and impossible. And luckily, actually, it worked out. so I managed to index, DBpedia abstracts encoded with BERT into Apache Solr and perform exact search on 1 million articles, and it worked reasonably well in terms of speed. I did not pay attention as much to the quality of search, like kind of whether it captures semantics, but actually on the surface it worked pretty well. Like you could say mathematics and it would answer algebra, right? And it's like, okay, cool. So there is some similarity. I understand what it's doing.
So I guess my first thing I want to, so there's a few things to that. So let me, first I want to ask about the integration between, like you said in the very beginning of what you're saying, is the integration of search as well as question answering and sentiment analysis. And that's one of my favorite things about Weaviate, getting to learn. I know you're familiar with all the vector databases, but I'm only really familiar with Weaviate, so I'm always going to be referring to Weaviate. So is the integration with the module. So it's like a search system, but then you can also append these supervised learning tasks onto it, integrate kind of the supervised learning functionality of like question answering, sentiment analysis with the text retrieval. And that's kind of what I was thinking about with your description of how to use these search systems with a deeper integration into the different kind of tasks you can do with these things. And then I love thinking about like multimodal data, combining images and text, videos, and all these different things, especially with like say biological data, where you can have all these different kinds of data and then integrate different supervised learning tasks and have this. So to me, it's almost like not even just a database, but it's like kind of like a whole platform for integrating all these different functionalities, I guess. But then, so then transitioning, could you take me through just like the overview of BERT and Elasticsearch? I read your article on Medium, and it's going to be linked in the description for viewers of this video. Can you take me through the quick introduction? I know you just did a lot of it, but going back to just the, like the TLDR, the overview of getting BERT set up with Elasticsearch.
Yeah, absolutely. So that was kind of a natural transition from Solr. Actually, I made another blog post on Lucene. I called it like Fun with Apache Lucene and BERT Search, something like that. Actually, the readers can find it on my Medium. Yeah, and then after that, I thought, because in my present company, we're using Elasticsearch. And I was thinking, okay, because now I kind of beginning to forget Solr after 10 years of usage, and I'm kind of plunging into Elasticsearch. And if you look at, kind of popularity behind these search engines, you could say it's not like there is a winner, but obviously Elasticsearch is backed by a commercial entity, and so they attract a lot of attention in the media and so on and so forth. And so I thought, okay, I'll give it a go, and I'll try to set up BERT based vector search with Elasticsearch. And I found out that actually they implemented dense vector type. And so essentially it's just a numeric vector which can store any floating point, numbers, sequence of numbers, and it could be integers as well. And they support cosine similarity, probably some other similarities as well, but at least that was enough for me to start. But one thing I figured quickly is that, first of all, because they didn't implement any approximate nearest neighbor search algorithm like HNSW or FAISS family, it was also like exact, meaning it takes big O n of n, of where n is the number of documents in your collection. And I think if you chop it up, in such a way that, let's say you have few millions per shard, I think it could still work quite okay. Of course, it depends on your SLA. Like in our case, queries per second was like 600. So, I mean, it probably wouldn't fly. So we need to have it like sub-second, you know. But in some other scenarios, it might be that maybe 600 milliseconds is okay, or maybe up to a second is okay, as long as you deliver the value to the user. And so I implemented quickly the exact search, and I measured the speed. And so I did like asymptotic analysis, actually, you know, where you can have different number of documents, and you also measure how long it takes to index, as well as how quick is the search, and also how much data there is on disk when you measure the index size. And then I thought, okay, is there anything else? And as I was punching my keyboard and writing the blog post, I was discovering also, okay, I was looking for other ways to implement it. And I found Alex Klibitz is the author of Elastic ANN. Hey, Alex, he's actually in my big ANN team. And he implemented LSH, locality sensitive hashing algorithm. And so that already goes, you know, step forward. And now you can have, let's say, 10 million documents indexed, and you will use approximate nearest search to find them and not suffer from increased latencies, right? So that was another system that I really wanted to try, learn, understand. It's sort of like, you know, the principles of LSH. Turns out there are different variations, different parameters you can tune. I've learned about Angular being another like way of representing the distance, and previously I thought it's just AngularJS, unrelated, but it's just the same term. And yeah, and then last but not least, at that point in time, I came across a blog post by GSI Technologies. So it's a US-based, California-based company which builds, you know, real hardware. And so they've built actually an engine, which is a hardware. It's like a chip which you insert into your server, and now it becomes like a vector database, right? And they use Hamming distance. And they have a proprietary neural hashing algorithm. And I thought, okay, you know, can I try this one? So I engaged with the sales. So the guy was publishing on Medium as well. And he was like, okay, I can give you access to it and you can try it out. And so I took GBpedia, a million vectors that I computed on my iMac, you know, which took me like, I don't know, 3-4 days of compute time. So, and then I've sent them the NumPy and a list of IDs, and they indexed in the server equipped with the device. And then basically I saw like, was it sub-second? I think it was sub-second search. I was amazed. And so then I built this asymptotic graph of, you know, exact Elastic and then GSI. And I also tried OpenSearch, which is a fork of Elasticsearch by Amazon mostly. Of course, it's open source, but mostly driven by Amazon. And so they implemented HNSW based on original C++ code. And that was interesting bridge between Java and C++. So I also tested out, and those of listeners who are interested, they can find all the details in the blog.
So could you take me a little more on the tour of, so I just recently became up to speed with HNSW, and that's the only approximate nearest neighbor search. I've been kind of familiar with FAISS before now, but I think if you could you correct my understanding, I think what it is it's exact nearest neighbor search, but it's parallelized pretty intensely. I think that's the core idea of it.
HNSW.
Or FAISS, sorry, for the FAISS.
Yeah.
Is that,
yeah, actually,
so that's exact neighbor matching, right?
FAISS is a family of algorithms. They implement, I think they implement like exact version, and then they have others, like HNSW is one of them, by the way, but they also have like, I think maybe the most prominent algorithm that also scales to billion level is based on product quantization. So essentially, when you have a vector, let's say it has 256 dimensions and you have floating point, it's a lot of data. So if you have billion vectors like that, it's going to like consume all your memory. and so basically what they do is that they apply a quantization technique where they can lose precision on the vectors in the attempt to bring you decreased latency, so increased speed, right? But they don't want to trade too much of recall, right? So your recall, and again, there are a bunch of parameters you can tune here and there, but that's like always a trade-off between QPS and recall. And they implement also inverted file. I forgot actually what it stands for, IVF. So it's like an inverted file data structure, which like you can try to, inverted index, TF, IDF, and BM25. These are the most efficient algorithms invented in like 15th century, right? And so, and that's the thing. How can you beat that in speed? It's basically like a keyword lookup, right? So it's a hash table. So you have keys. As keys, you have the terms, and then as values, you have posting lists, which are ordered sets of doc IDs, right? And so, like Lucene made it super, super efficient. Now, how can you, if you have a vector search, you cannot do that anymore, right? You don't have a lookup table. And so that hence all these approximate nearest neighbors algorithms kind of kick in. And so FAISS is just one example where they invented like a code book where they try to map, your vector into like lower precision representation. And by doing that, if you have some vectors which are close to each other semantically, they may end up, being mapped to the same point. And actually, LSH has a similar kind of issue, right? And so there are some techniques to also combat that problem. So for instance, let's say first step, you will do approximate nearest search and you over query. Let's say if you want top K, you say, give me top 1,000, just for the sake of example. And then you get that top 1,000 and you know that because of that loss of precision, there will be shuffled order somewhere, most likely, right? You just go to disk, and let's assume you have an SSD disk. You can actually reshuffle these vectors by loading the original high precision version of each vector and just sorting by distance then, right? And so this was proven by Microsoft actually in their paper Disk ANN, that you will achieve like better results than just product quantization or HNSW, and you will win on memory as well.
Yeah, that reminds me of like mixed precision training algorithms where you have, say, 32-bit floating points for usually your weights, and you store that, and then you train with 16 bits, and then you have the 32 bits still ready for the update if needed. And yeah, the mixed precision thing is super interesting. I love seeing, like, it seems to me like the mixed precision in deep learning training workflows is almost like free lunch in the sense that you don't really have to worry about it messing up the training. And then when I was reacting to what you were just saying, I was thinking, well, if you reduce the precision and then they're the exact same vectors, they were probably pretty similar to begin with, right? Like you're not reducing it that much that it would like lose that much information usually. So I don't see that being an issue with this. But then to kind of backtrack a little bit on this idea of the inverted indexes and say the symbolic filters. So something I really love about Weaviate is the way that they're looking at the symbolic labeling of the vector data as well as just storing the vector. So you have in their news articles example, you have the publications they were published in. So you have, say, the New York Times, the Financial Times, the Wall Street Journal. And so you have these symbolic filters that usually you would store in these inverted indexes to then go into, like say you had a binary tree on the IDs of the, or not a binary tree, but you have some kind of structure of the IDs of the documents. And so is that a setting where, so how do you see the interaction between the symbolic inverted indexes and then the ANN algorithms like HNSW or locality sensitive hashing on the vectors that are then filtered from the symbolic filtering? So really quickly before you dive into it, I was talking to Eddie yesterday about the same topic, and the HNSW tree graph, it seems that you don't really change the search based on the symbolic filters too much. It's just like a way of how many nodes you have in the frontier of, say, the breadth first search on the graph.
In HNSW, basically, you can like control the parameter of fan out, right? So basically, you say, okay, the way this works is that HNSW will split your data in different levels of coarsity. So basically, the top level is the most coarse, meaning that the distances are the longest, right? It's almost like thinking in terms of geography. Let's say I want to fly from Helsinki to New York, right? And I have a specific address there, and I have a specific address here as well. So first I need to drive to the airport. That's like a shorter distance. Then I fly over the ocean, and that's like a long distance flight, taking 7 hours. And then once I landed in JFK, I would like to go to a certain address on Manhattan, right? And so so first things first, I need to fly over the ocean, and that's the first layer of HNSW, right? So I'm looking for the nearest neighbor to sort of fly to New York, and that's my airport. And then I basically I transition to the next level of the graph where the distances are shorter. Now when I'm in JFK, I can take a train or a cab and go to Manhattan. So that's a shorter distance, right? And once I'm on Manhattan, or certain station on Manhattan, I can go to the third level and now kind of look more precisely where is it that I'm going. And so that's the intuitive explanation that I can offer. And yeah, so essentially you can then still control the fan out. So from the airport in Helsinki, I could have flown to Munich instead of flying directly to New York, right? And there could be more carriers going to Munich because Munich is like a hub by itself. So I go to Germany and I wait a couple hours, chill out in the airport, and they then fly. As I am saying this, it's very like strange to say because I don't fly now, but still when we used to fly. And yeah, and then basically I could also maybe go back to Moscow, which is kind of a bit counterintuitive, but I could also backtrack to Moscow and fly from Moscow, right? So there are multiple opportunities the way I could fly. I could also make a layover stop in Iceland, right? So it's like there are multiple opportunities. So the same happens in HNSW because it doesn't know exactly where your approximate nearest neighbors will be or exact nearest neighbors will be. So it just tries to, find few entry points on each level and then kind of multi-thread from there, right? And so as you do that, you can then actually examine some labels. I would be curious to know how Etienne explained it, how they do it, because this is something I still would like to learn myself. But basically you can examine the labels or values in those vectors, right? Because in Weaviate, they store the vector index as well as the object index and then the inverted index, right? It's basically tri-index sort of database. That's a smart thing to do, I think, because you will never have a situation when you will have data drift between these two or three, amongst these three. So yeah, so I mean, basically then you can kind of, as you said, you can limit the space in which you go, but in HNSW, I don't think you can, without some customization of that algorithm, you cannot say, give me another list of neighbors that satisfy also this criteria, because it will kind of defeat the purpose, right? You want to do it as quickly as possible, but I think Etienne might have shared some interesting insight on that. I'm curious to learn that.
Yeah, so if anyone is interested in this also, we also recorded this podcast and uploaded it to YouTube where Etienne explains this, and now I'm going to botch it and me regurgitating what I learned from him. But it's something to do with when you have the frontier of the nodes you're exploring as you're traversing the graph, like Dmitry said, as you've flown from Helsinki to New York. Now you're in New York and you're looking at Miami, Austin, Los Angeles, and say Seattle. You would use the symbolic filter to X out some of those paths and not take that path. So now you're going to Miami because you said you want to go to somewhere sunny, like a symbolic filter like that, compared to Seattle, or I guess Seattle is sunny. It depends on the year, but with that kind of idea of using the symbolic filter with respect to how you're exploring the frontier. But again, I'm not sure that's exactly correct. So the podcast I have with Eddie, and he explains it in great detail, and it's the video is chaptered up if you want to just jump ahead to that exactly. So to transition a bit, can you tell me about the design of these approximate nearest neighbor benchmarks and kind of like what they're looking for? Is it like you have an exact match vector and then you just add some noise to it and then you say, can you find what this originally was, or is there something else to it?
I mean, it's relatively straightforward, and both ANN benchmarks and big ANN benchmarks, it's almost the same team that is doing this, with few exceptions here and there. So the idea is that you have a number of data sets, and for these data sets, you have samples of queries, and then for those queries, you also know the ground truth. So you basically know exact 10 vectors that correspond to these queries, right? How exactly they did it, I don't know. I haven't been drilling into that, but essentially, you can kind of, let's say it's a human annotator labor or something like that. Now, or you can actually run an exact KNN search, and you can just figure out, okay, using this distance metric, let's say Euclidean, what are the top 10 exact neighbors to my query, right? Now, as you try your algorithm, you will use maybe approximate nearest algorithm, right? Now you can basically also request top 10 documents or vectors from your database using your algorithm, and now you can overlap the ground truth top 10 with the top 10 that you have returned from your algorithm, and you can compute the percent of overlap, and that's your recall. And so as the closer it is to 1, the better, right? Or 100%. So and then it becomes like a trade-off between QPS and recall, because usually you will have like, at this QPS, I got this recall, right? And there will be some kind of line which might be kind of dropping over time, not over time, but over QPS. As QPS is growing, basically, if we bombard our database or algorithm with the queries, at some point it will kind of choke or like give up, and it will not process that many queries, right? But you can also vary the recall parameter, so you can say, let me make my algorithm less precise, right? Now I can probably make it faster, right? And in some situations, in certain use cases, maybe there will be cases where 60% recall is okay, right? Maybe it sounds strange, but maybe it will be okay. Or 70%, like you don't need 100% in certain situations, right? Like you're looking for similar items, and then you can go and explore, the space of similar items, take some action there.
Yeah,
so, big NN is very similar. It's just the scale is different. It's like 1 billion.
Yeah, it reminds me of like information retrieval, and say like how you might have like a supervised learning task on the ranking part of the output from the information retrieval. So you might make it like a 2-stage system where the information retrieval returns 1,000 documents compared to 100 or 10,000 on that kind of scale. And that's the input to the supervised learning re-ranking model, and that kind of idea of having that pipeline. So how, my question as I'm kind of getting up to speed and learning about these approximate nearest neighbor benchmarks, why is it called something different from information retrieval? Because like that term information retrieval, I think clearly communicates like the task, so to say, with the deep learning research. Why is approximate nearest neighbors holding a different name?
Yeah, it's a great question, Connor. I mean, the way I see it is that, like nearest neighbor algorithms, they have been developing in parallel with information retrieval. I actually have a friend who he did his PhD in this topic. And as I was digging into HNSW, I found a citation of his paper from 2009. And at that point, I was like, wow, so now these paths have intersected. And as researchers have been developing these algorithms, they've been applying them to arbitrary objects. So it wasn't really related to kind of textual information retrieval, like more familiar to us. You could encode any object, and it remains to this date, right? Like basically you can encode, images, videos, audio signal. You could even like encode an email, right? So let's say you have a subject, you have, two lists, CC list, BCC, and so on, and you want to model it as a single object. You could also encode it as a single object into the vector representation, and then look for similar emails, right, on a number of dimensions, not just text. And and then over time, now that there've been a lot of research and like, okay, I can study my genome and I can encode some similar patterns in the genome. I'm not a professional in this area, so sorry if I'm misusing the terms, but let's say now can we apply the same technique to text? And if you listen to the podcast with myself and Bob Van Looyd from Weaviate, or from Semi actually, building Weaviate, he was actually explaining how he came up with the idea of Weaviate, that he took GloVe, framework, and he was trying to make sense of sentences that would be similar to each other. Let's say when you query with the word apple, it would know that apple might mean a company, but also a fruit. And so it worked reasonably well for him, and he saw the potential. But then BERT came out, right? Attention is all you need, and now you can encode your text into a vector representation using a huge language model, right? And it knows a lot about things. By the way, one thing that struck me recently is that BERT doesn't understand negations, but maybe we shouldn't go there yet, but it's just something that where research might take us, that we need to kind of embed knowledge into language models. But still, it does a reasonably good job. And I mean, Google used a language model to improve relevancy for 10% of their longest queries, right? So like queries that look like sentences or questions. And this is where things kind of, I think, turned in the direction, okay, can we apply similarity search to text? Yes, of course we can. Can we do it at scale? Yes, we can. What is stopping us from deploying this to production? Nothing. We can develop vector database, offer it to our clients, and off we go, right? And this is where things began to happen. And I think this is exactly why, like, ANN benchmarks, they still continue to push the idea that it might not be text. By the way, in big ANN competition, they have released the data sets, but they don't tell the source of the data set. It's just a set of vectors, right? And some of these data sets are much tougher than the others. Like some of them, they actually say it's probably like text to image, but like something else is just very cryptic. You don't know what it is. Then you run your algorithm, like I ran FAISS on one of them, it just doesn't work. Data set is way too hard, and I don't even know if it's text or not. I don't care because the algorithm doesn't care, right? All I care is about tuning it.
Yeah, maybe like the hospitals would like something like that, where you can just send your vectors in and no need to like try to decode it. I imagine you couldn't decode it, but I guess somebody could figure out. Yeah, so there may be like three things I wanted to touch on with what you just said before transitioning into our next topic. And the first, just quickly, you mentioned the negation that BERT can't handle not, and this is kind of a research topic that I'm really interested in. So I just want to quickly talk about it. Like the use of, say, data augmentation, consistency, and contrastive losses to mitigate robustness is something that I think will have a huge impact on these vector similarity search engines. So like Dmitry just said, if you add, say, we did not go for a walk compared to I did go for a walk, you might get a pretty similar vector representation. And that's obviously super problematic for what we're talking about here. So the kind of area of research that I'm looking into and looking to develop is, say, we have all these data augmentations where you insert the not, or, you change so you have a named entity and you swap out the named entity. And so I think particularly the difference between in images, data augmentation has been really successful because it's very easy to be label preserving. You rotate an image, you horizontally flip it, you increase the brightness, you're not going to flip the label. But with text data, it seems like it's much more likely, it seems easier to design data augmentations that flip the label than would preserve the label. So, and then I think the contrastive learning consistency losses, those are kind of the two interfaces I see to better integrate data augmentation and solve this problem that we're talking about of having the vectors be, similar, even though they're describing the opposite things. And so then the second thing quickly to touch on is in the information retrieval difference between ANN, it seems like maybe one other difference is that you kind of have say this is a query and then these are documents. So maybe that kind of gap between the semantics of the two things you're encoding, whereas it's like these are all documents compared to you're kind of transferring from query to the space of document encodings. And that's kind of like a supervised learning task that maybe deserves a different name for information retrieval compared to ANN, where it's all the same like category. And yeah, just all this idea of like other data domains other than text. Like we have graphs, like say you're looking for a similar neighborhood across the entire world that has a similar graph structure with, say, distance to other houses, the grocery store, the gym, and stuff like that. And you want to look across the entire world where you have billions of graph structured embeddings of local neighborhoods. And then, video data to, where you map all the queries to Henry AI Labs videos and that kind of thing. So anyways, so to transition to our next topic. So Dmitry wrote this really great article, Not All Vector Databases Are Equal. And I really love this article because to me, I just think it's so interesting, like this vector database space emerging. And it seems like you're right at the cutting edge of it and understand the difference between these cutting edge things. So can you kind of take us through like maybe like levels of this, like level one, the high level description of how these different implementations of vector databases differ? And then we can kind of like go into more granularity from there.
Oh yeah, for sure, with pleasure. And I'm sure we can link in your show notes the blog post itself. I've been inspired by a thing that ThoughtWorks has been working on. So it's like a technology radar. Have you heard about it?
No.
So Tech Radar, and we can also link to that. Essentially, it's like as you go in the industry and you solve certain problems, technology problems, you need to choose these technologies, right? And these different technologies, they have like different level of maturity as well, right? Let's say my SQL database has been used for years and years, and it's like a, known tool to everyone. There is like little room that it will fail. Maybe it will fail at scale, but that's another problem to solve, right? But then if you pick, let's say, I don't know, some agile methodology, how you want to structure your development process, okay, which model you should prefer. And that's like a gray area and like an area of research. And some other technology might be like a new kid on the block. So you don't have the maturity in it, but you might have some promise that it will address certain issues you came across, and you've been kind of inventing the wheel to solve them, right? Or reinventing the wheel. And so I've been inspired by Tech Radar, but one thing I didn't do in this blog post, I actually didn't label the databases on the maturity, because in my opinion, this area is still emerging, right? And so you could say largely every database in this list is like a new kid on the block. and so so essentially if I drill down into the blog post, I've been focusing on value prop. So something that captures my attention as a user, right? Some kind of wow effect. Then what's the type of this database? Is it managed, self-hosted, both? Or sometimes it's like basically they offer you the open source version and you need to figure out how to host it. And they might also offer you some algorithms to scale it. Then I also focused on the architecture. So in the architecture item, I paid attention to kind of like system level architecture as well as feature level architecture. So for instance, in Weaviate, as an example, we have like contextuaries, we have some other modules there. We have the algorithm, which is pluginable, so you can also implement your own ANN algorithm as a plugin. So that kind of as well tells you, okay, if in the future I will need to customize this database, can I do it? Then I also focused on the algorithm, kind of like the preferred algorithm, if it exists, ANN algorithm, or if they offer kind of like a suite of algorithms. And then the code, is it open source or closed source? And so from 7 databases that I have here, so if I enumerate them, that's Weaviate, Pinecone, GSI, APU, Milvus, Vespa, Vald, and Quadrant. So of these 7 databases, 2 are, I believe 2 are closed source, yeah, so that's Pinecone and GSI. Every other database is open source. So you can basically go and check some of the hypotheses you might have, or if you want to read in the source code closely, then you can do that. And so, yeah, so basically these have been the levels of what I considered, so like 5 levels: value prop, type, architecture, algorithm, and code. And essentially every database block, it's like no longer than a page where you see all of these items. You see, a link to the open source repository if it is an open source, and then you have an architecture diagram. And many of these databases, so I actually reached out to the makers, to the owners or developers of these databases, and I said, okay, can you give me maybe an architecture diagram that might be kind of a little bit like exclusive for this blog. In some cases, they referred me to the existing documentation. In some cases, they actually even invited a designer to build the more better looking architecture diagram from some kind of sketch. And I think this also helped them to present themselves better. Um, and yeah, so basically, I also focused on things like, for example, if I'm talking about a wow effect, let's say in Milvus, the wow effect for me was that you can index your data with different ANN algorithms, and then you can compare the search right there. So it's like amazing. And they also focus on scalability a lot. In Pinecone, I think the fact that it's fully managed database, so like it's zero friction to deploy it, right? So you don't have to manage it, you don't have to set it up, just send the data in, start, it will index, and then you can search for it. That's amazing. But they also support like FAISS as one of the algorithms, and then they have some proprietary algorithm there. So I mean, for some of the clients and use cases, this will be the choice to go for. Then Vespa, I think Vespa is a huge database. I'm still learning some parts of it, but it's not just the database. It's also like a platform, like a data science platform,
Oh,
and it's deployed at scale. And yeah, I mean, they have some really cool deep learning like data structures like tensors. So they support tensors, as first-class citizens there, and that's amazing. And then the algorithm there is HNSW, which was also modified for CRUD. But they also focus a lot, and you touch on this corner. They focus a lot on re-ranking, right? So using dense retrieval methods, and basically they have really great series of blog posts where they go deep into how you can train a re-ranker and what are the implications. Then Weaviate, hey Bob and Etienne and the team. So really, it's both managed and self-hosted database. It's open source. It's written in Go, and Go is actually a really performant language. And the wow effect for me when I saw the first presentation by Bob on Haystack Meetup was the GraphQL interface. And I was like just blown right there. So the things that I was thinking, how can I do in Apache Solr or Elasticsearch, with like syntax that was probably not meant for this. It's an inverted index search. You have faceting, you have like scalar filters, right? But like you cannot say something, give me all the companies that were bought by IBM and are, in this space, let's say in healthcare. Like it's really hard to make such query. You need to build your data structure. You need to do something up front in the index to solve this. While in Weaviate, it's a native interface, and I was just amazed by this. And I think this question answering component is also like a wow effect for me. Yeah, and in terms of algorithms, so they implemented a custom version of HNSW. So the graph algorithm, it's tuned to scale to support full CRUD, and they also have a plugin architecture where you can like bring in your own algorithm. And they also support like different languages. Let's say if I don't code in Go, I can continue coding in Python and bring in my model, and essentially because they use like Dockerization and everything, like you can do it, right? And then I was like, is there anything else? So I was looking on the web, is there any other search engine of which I can classify as a vector database? And I was kind of like, am I running out of options? And I came across Vald, and I was like, wow, what's that? So that's like a self-hosted vector search database. And the wow effect there is that they use the fastest algorithm called NGT. And so
And
yeah, so basically it's faster than Google's algorithm. It's faster than HNSW, and it's developed by Yahoo Japan,
wow,
guys.
yeah.
And I what I did is actually, because I knew nobody from that team, I just went on their GitHub, opened an issue, and I said, "Hey guys, I'm writing a blog post. Can you help me?" And they responded almost immediately, which was like also showing the passion of the team. And they also have Slack, and I joined it, and from there it's history. So they also gave me the nice diagram there. And not last yet, GSI APU. That's another commercial vector database offering. In fact, this is a hardware-baked associative processing unit, which searches for vectors using Hamming distance. And yeah, so essentially it plugs into Elasticsearch or OpenSearch. So they have a plugin which then talks to their APU backend, right? And yeah, it's offered as on-premise, as well as you can actually, so basically you can like buy the board, the APU board, and install into your server. Or you can use the kind of like hosted cloud backend. And I think at this point they are partnering with Amazon to push this forward. And so I had a chance to test it, and there is another blog post on this. I already mentioned it, so it's pretty interesting system. And then I published this blog, and Greg Cogan from Pinecone, sent it to Hacker News, and it was almost my night. And when I woke up, there was like 15,000 views of this blog, and I was like, "Oh my God, what's going on?" So that's like the maybe the power of Hacker News, but it was also the timing. I can never figure this out, like the timing when you need to post this blog. I think Connor, you experienced the same.
Oh yeah.
So like, should it be Tuesday afternoon? Yeah. So things like that. I don't even remember which day it was. I think it was Friday night, something like that. I need to look it up. But yeah, and so it stayed in the top, I guess, was it 100 or however many news items there are on Hacker News. And it stayed there for like an hour or more. And that's like a lot.
Yeah.
They have like hundreds and hundreds of links being sent per minute, I guess. So it's super popular place. And then there was one guy knocking on my door. Actually he not yeah, figuratively, he left a comment on my blog, and he said, "Hey, we are Quadrant," and he used my structure, right? So he said, "This is the value prop, this is the architecture, this is the algorithm, blah blah blah, please use it." And he left it as a comment. And I was like, okay, maybe I should wait. Maybe somebody else will knock on the door as well, and I will just edit at the same go. And then he reached out, and this database is called Quadrant. So he reached out on LinkedIn, and he said, "You know what? Actually, we are raising the seed round for our company, and our investor has asked us, why are you not on this blog post?" At that point, I was like, "Is this really going on? Is this really?" I didn't plan for this. My goal was to satisfy my curiosity, nothing more, really. But I'm really glad that this also helps the community. And if this blog post is now like a role model, how you should describe your database, fine by me.
Well, yeah, I mean, the article is brilliant. The timing of it is amazing. And I mean, first of all, before I start saying anything, thank you so much for everything you just described. I mean, I learned so much just in the last 10 minutes of just sitting here and making some notes of what you were saying. But yeah, I mean, it reminds me of, say, like hyperparameter optimization and MLOps. Like, well, I guess MLOps is like a bigger thing. I don't mean to say it's just hyperparameter optimization, but like it reminds me of, say, like the hyperparameter tuning in the early stages of that, where it was like you have all these different things, and it was like this hot space. And it reminded me of when you mentioned like Vespa having the ML ops kind of, or like, all the data science, like the experiment tracking and the visualization, all that kind of stuff, like a part of like the vestigial of it as it's evolving into now vector search engines being kind of like a new category of this like deep learning technology. And yeah, I mean, it's super exciting. I can definitely see it being on Hacker News. It's like such an exciting new sort of like emerging industry. And it reminds me, and I mean, MLOps looks like it's so successful. So it's like, it seems like a good thing to be looking at. So, okay. So some questions, I got 6 questions for you from what I was just listening to. So firstly, the NGT you mentioned quickly, better than HNSW. That's, we can't pass over that. Is that benchmarked on the ANN benchmarks, and that's how it's determined as
It
better?
is, yeah, it is. You can, of course, it's not like on every data set, but largely it beats like many algorithms. And yeah, it's like on million scale. And I know the same team has submitted to billion scale as well. So I'm looking forward to the results.
So it's completely closed. There's no archive link or anything that describes what's happening.
NGT is open source, so
Oh,
I can
okay.
also provide a link to it. I think it's written in Rust or C++. I need to check it, but the idea is very interesting. And they support a number of languages as well. So they have interfaces to it, like in Python, Ruby, Go, Rust. And so, yeah, it's a nice algorithm to take a look at. And there is a paper as well, I think. So yeah, there are a few papers there.
Super cool. So then the next thing is, so the self-hosted versus where one of these companies hosts the data for you. How do you see that as being? So like you're basically saying, surrender my security to you to host it, right? That's the big value proposition that they're proposing when they say, self-hosted uh, what is it? It's self-hosted versus what do they call it when they host it?
Managed.
Oh, man. Oh, okay, right. So then when they say managed hosting, they're saying, we'll take care of the security of your data for you.
Yeah, I mean, it's not only security, and security is actually a very important topic to cover. But I think the biggest selling argument in using the managed database is that, if your company doesn't want to hire engineers who will kind of just scale it and kind of keep installing and fixing bugs and upgrading it, and it's a
Yeah,
lot
yeah.
of
Oh,
work.
yeah.
Like I've been going through this with my team for the past like 10 years, like upgrading Apache Solar. You learn a ton, but also, are you focusing on the right thing? Like maybe you could have implemented some new cool search features like that. But then again, some companies, and that depends on the company culture, some companies really take pride in owning the tech stack end to end. So they really want to know everything, how it's written. Maybe they want to customize it. I remember at some point, I think it was Berlin Buzzwords Conference, one of my favorite. I met a book author on Elasticsearch, and he wrote kind of like a dedication, or how do you say it? When they give you a book and they write like good luck in search or something. So he wrote, and his name is Rafal Kutz. So he wrote, if you do not find the answer in the documentation, go read the source code, right? So that's like, some companies do take pride in that. Some other companies, they might just say, okay, I have a product idea. I don't have time to figure out all of the details. Now, can you also offer me the security? For instance, SOC compliancy, SOC 2, let's say you're a bank, right? And you have some custom proprietary research. You don't want to like leak that. So now, if you're SOC 2 compliant, it means that you can actually prove that you have processes in place. It's not just the database itself, it's also the processes, it's also the usage of licensed software, which licenses do you use, and so on. Then basically, can you prove that you provide a secure enough environment? There is no 100% security, but secure enough, right? And another like argument is that, what if you have an idea and you can just go, let's say you are AWS user, you heard about Elasticsearch, you don't know how to install it, you actually just want to try it. So you can model it as an API, right? And this is what the Weaviate is doing, this is what Pinecone is doing as well, and a few others. They just model it as an API, right? And so does it matter if this API backend sits on your servers or if it sits like somewhere close that you trust and it's like encrypted and scaled that you are using, right? So the answer is like on the client side usually.
Yeah, no, I mean, here I go again with I've been including making sure I describe this in every Henry AI Labs Weaviate video I do again, but one more time just for everyone because I love this idea. And we see this trend where papers with code started organizing the benchmarks of deep learning papers and the new results that they're posting in the new papers. And now that's evolved into an organization of data sets that is extremely interesting. We have, say, Hugging Face data sets, papers with code, papers with data, and we have, say, Kaggle compositions that have been around for a while. But this organization of all these data sets, and then this idea, as Dmitry mentions, the managed hosting, where Weaviate is hosting these data sets and taking care of all that backend. And so it just lets us kind of researchers, say like academics interested in the algorithms, just grab the endpoint, and then you can do vector search without having to have engineering skills necessarily, to be really managing and updating the latest release of all of these deep learning data sets that you might want to do. You might want to be like doing transfer learning with all these different natural language processing data sets, multimodal learning, connecting just two different data sets, image, text, whatever it is, as we imagine like what this might look like in 5 years of organizing all these data sets and then having these managed endpoints. So you mentioned the GraphQL of Weaviate, and personally, when I first saw GraphQL, I didn't understand it until I started studying Weaviate, and now I kind of have a sense of it. So what was your experience with GraphQL prior to Weaviate, and have you used it before this, or is it like kind of similar to me that the kind of understanding the symbolic filters is how it helped this kind of the use of GraphQL and why it's different from a REST API click?
Yeah, so GraphQL we used at AlphaSense. It was driven by another kind of team lead who kind of introduced it to the team, and he was like the promoter of it in a way, right? But the idea, the fundamental idea, the way I captured it is that as your product evolves, and let's say you have an increasing number of teams, and what you want as a, let's say, vice president of engineering, you want to have some loose coupling between the teams, right? So that they can run as fast as possible and deliver the value. But what does it mean in turn is that they will be messing with the code base and they will be changing the data structures. They will be changing the indexable items and so on and so forth. Now, at some point, everything converges to the same pipeline, to the same API. It's the same product, right? And we've been building the same product essentially at AlphaSense. And as your data evolves, the number one question is, when I'm releasing something, is it backwards compatible? If it's not, it's going to break somebody's experience. Somebody is going to call you and say, I'm raving, I'm going to call back all my seats. Now, GraphQL allows you to kind of introduce some data point in the database and then kind of flexibly introduce it on the API layer without breaking everyone else's use case. Okay, so you can say, if yesterday I was retrieving articles with titles and authorship, and today I changed my mind and I introduced a summary field, right? Mm-hmm. I would like to get the summary field, and I'm just saying to GraphQL, hey, could you also include the summary field, right? Mm-hmm. And as long as it exists there, it maps it back to the index side. It will retrieve it. If it doesn't exist, it won't. So if we didn't manage to upgrade all the databases on the backend in production by the time we rolled out this change, the summary field will not go back. You will not see it in the response. It's okay. So now, of course, you need to have some handling in the code that if I didn't receive it, then what to do. But in general, it gives you so much flexibility. So basically, like, you can be backwards and forwards compatible, which mm-hmm. is like it's the paradise, right? Of course, it's not that kind of rosy all the time. There are certain situations when maybe you run into complexities and maybe GraphQL looks unnecessarily complex, but the complexity that it brings gives you so much power, right? And so that's what Facebook has figured out when they implemented it. And I mean, because at Facebook scale, they needed to run, their motto was run fast and break things, right? Then at some point they turned it into run fast and with stable infra, right? So they wanted to not break things as much. And so, yeah, so I mean, the same holds for any search engine, right? So if your search engine could also expose the GraphQL-like interface, then you wouldn't need to code the same logic on your client side or in your business logic, right? So you would leverage that level. And so I think Weaviate is doing a smart move on offering it, even though I don't think Bob and his team are doubling down on GraphQL necessarily, but I think it's a sexy feature that in the future might be a deal breaker for some of the clients.
Super interesting. So yeah, so then just one more, just two more things. So to quickly touch on just the Python client, I think it's, this is super cool, and this is something maybe we'll talk about later. Is the Python client lets you say integrate the back end of your vector search engine into your current workflows. Maybe it's a deep learning training workflow, and I think there are a few research ideas around how you could maybe use this within your existing code and thinking about the integration with the Python API. But then just a last question I want to ask you about building custom hardware for vector search engines, and generally pioneering this. Not all vector databases are equal, and kind of having a quick thumb on this emerging space. I'm curious what you think about like custom hardware for the deep learning applications and how that will kind of play out.
Yeah, that's a great question. And I mean, in this part, of course, the only custom hardware I know about is built by GSI Technologies, and so they built APU, Associative Processing Unit, and they have proven that by using neural hashing technique, that you can actually like downscale your vectors in some new representation that will allow you to save space as well as memory. Then in the downstream, they use Hamming distance, and so essentially they turn any vector, let's say floating point integer, into a binary vector. So they basically build a neural network that converts your input vector into binary representation, and now Hamming distance operates on binary vectors, right? And they have proven that there won't be a loss in precision, right? Like if the loss is there, it's compatible or comparable with, let's say, FAISS or HNSW, right? And why build custom hardware? Well, actually, we touched on this previously. Let's say security, right? What if you don't want to use a managed database, and you have some existing beefy server? How can I turn that into the vector database? So GSI offers an APU card board that you can plug in, and for billion scale, you need like about 3 to 4 boards, better 4, that you can install on your server and essentially scale to billion level. If you're not on billion level, you might use 2 boards and be done with that. Now, what the GSI is focusing on also, which was also a discovery for me, their clients are in defense and also in space. And so actually, when you go to space, the same hardware as your computer or your server will stop working because of abnormal temperatures, because of radiation, because of something else flipping the bits, right? And so they have implemented hardware that will be resilient to these, signals or impacts. And now you can run your vector search on a satellite. Can you imagine that? So you might have, you might rent like Elon Musk's satellite and then install an APU board and run your vector search somewhere in space. You will not have problems with cooling probably, because it's damn cool there, I guess, but not all the time. Sometimes it's damn hot as well. So anyway, so that's just one thing that they are doing there. And they are also applying, the roots of the company also comes from like remote sensing and like spectrography and some other areas where they have been developing their hardware for a long time, and they figured out that, okay, they are a hardware company. Can they actually ship it as a hardware and not venture into, software business necessarily, but they can like partner with Elasticsearch or OpenSearch, and maybe in the future, all of these vector databases can offer APU as one of their backends, right? So that's the thinking here.
Well, thank you so much, Dmitry, for everything. I mean, I learned so much in this hour, and I'm sure people will like this kind of stuff. So, if you have any questions for Dmitry has the Vector podcast on YouTube. You can find him on LinkedIn. Is there anything else that you'd like to share a link to find you?
Yeah, for sure. So Medium blog is one way to kind of follow. You can also reach out and follow me on Twitter. I'm relatively active there. So
awesome. Thank you so much, Dmitry. This was great.
Thanks, Connor.